Hello, I am Grayson Light. I'm from the University of Cincinnati, and I will be presenting a light intro to differential geometry with a new type of Riemannian submersion. This research was done with Dr. Jem Sayar at Florida International University, and let's get started. So first off, why do we care? Why do we care about submersion theory? Well, because this is the Society for Industrial and Applied Mathematics, let's go into some of the applications of submersion theory. The first being Kaluza-Klein theory. This is a classical theory combining like gravitation and electromagnetism in physics. Indeed, it uses submersion theory as well as machine learning. There are also MRI, like medical imaging applications too, as well as stats and modern robotics. So indeed, these applications do exist, and it is worth looking into submersion theory in general to find more applications. So let's get into the preliminary stuff before we can get into the actual meat and potatoes of this talk. So first off, everything that we do is going to be done on smooth manifolds. We can think of them just as like surfaces in R3, with the smoothness coming from these transition maps right here. These maps must be smooth. This is somewhat technical. For the purposes of this talk, all we really need to do is envision manifolds, smooth manifolds, as surfaces in R3, like spheres. Speaking of spheres, here's a sphere. We know on this sphere, for any point P, we can draw tangent vectors through that point P on the sphere. This is done by taking some sort of arc that intersects the point P, and then taking the derivative of this as that arc approaches the point P. Okay? We can put all of these tangent vectors into a plane called the tangent plane, denoted TPS2 for the sphere, or a TPM for the general manifold M. And kind of waving my hands here, the union of all of these tangent spaces, of all these TPMs across the manifold, is the tangent bundle, denoted TM. Now, if we want to kind of generalize these tangent vectors, we can consider vector fields. Vector fields are these mappings across a given manifold where we can plug in a point and then plug in a sufficiently smooth function, we denote it f in the specific slide, and get a tangent vector out of it. With this picture here, we can envision a vector field like so. Vector field x, we can take a point P on our surface, say this point here, and then we can plug in some function f that's sufficiently smooth to get this arrow, this tangent vector, out of it. We can do this across this manifold, this surface. Okay. Now, for our purposes, we will need distributions, and for us, distributions will be considered as like spans of vector fields that still lie in that tangent bundle TM. Okay? All right. Now, everything that we do is going to be done on Riemannian manifolds. What are they? Well, they are smooth manifolds that have this really nifty map G. This is called the Riemannian metric, and it behaves, in practice, pretty much identically to an inner product. Okay? What this is you take two tangent vectors, or maybe two like vector fields, you plug them into G, and it gives you some sort of number out of it. You can think of it like a Euclidean inner product, okay? Like maybe your smooth manifold is your sphere, and your inner product could be seriously just like an inner product between two tangent vectors in the R3 sense. Excuse me. Now, because this Riemannian metric behaves like an inner product, we can define stuff kind of in analogy with this inner product, such as a norm. Like this is defined in analogy with the Euclidean norm. We can also define angles. That'll come a little bit later, but we will be using Riemannian manifolds for the remainder of this talk. Now, the last kind of general technical thing is the push forward. So for our talk, we're going to denote all of our maps from Riemannian from manifold M to manifold N. We denote them as pi. Okay, and for this map, sufficiently smooth, we can define something called the push forward, pi star. For us, we can say that pi star takes a vector field on M and then maps it, pushes it forward to a vector field on N. And it follows this relation at the bottom here. This is a fairly technical result that we don't super need. We're going to need it when making a matrix later, where h, by the way, is just some sort of smooth function on n, and p is a point on m here. This equation right here is a nifty way of evaluating the push forward when plugging in a given function. But again, we don't necessarily need this. This is mostly just used when creating our matrix later. Now, we'll get into the matrix in a little bit, but let's define what we need. We need Riemannian submersions. Riemannian submersions are these mappings between Riemannian manifolds. For us, we're always going to call the manifold that it maps to, the manifold that it maps from, M, and the manifold that pi maps into, N. Okay? Now, pi, being a Riemannian submersion, has three very nice properties. One, it's surjective. It's great. But the other two, a little bit cooler. So pi has maximal rank. What does that mean? Well, pi star is a linear mapping. That push forward is linear. And by taking bases for your manifolds M and N, you can write pi star as a matrix, as I was talking about earlier. If this matrix has maximal rank, then this first property is satisfied. Pi has maximal rank. The second one is a little wordier. The push forward pi star restricted onto the horizontal distribution, kernel pi star perp, is a linear isometry. That's a lot of words. What does all that mean? Well, let's delve into this kernel pi star perp thing first. The idea of a Riemannian submersion is to map from a bigger manifold, M, to a smaller manifold, N. What do those words mean? It's just the dimension of your manifold. We can think of an example like a map from a sphere to a circle. Our big manifold is the sphere, dimension 3, and the small one is the circle. Now, when we map with that push forward, when we map a tangent vector from that sphere to the circle, we lose a dimension. The tangent vector in R3 has 3 components, and in R2 it only has 2 on that sphere. So what happens to those components that kind of get washed out? Well, this is exactly the kernel of your push forward, kernel pi star, and we call those the vertical vector fields. Kernel pi star perp, on the other hand, we call those the horizontal vector fields. These are the vector fields that are orthogonal to all those vertical ones. Orthogonal is defined exactly like it is, kind of like in R3 with the typical inner product, okay? If you take any two vector fields, plug them into the Riemannian metric G, if they evaluate to 0 everywhere, then they are called orthogonal. So these horizontal vector fields, kernel pi star perp, these are all orthogonal to the vertical vector fields in kernel pi star. Okay? Now, this linear isometry part is actually quite a bit simpler. If you just take any two horizontal vector fields, x and y, you can kind of drop this pi star if you push them forward onto the base manifold n, the little manifold n, and then you plug them into that manifold's metric, you can just drop pi star. It's pretty nice. So yes, this is the Riemannian submersion. And then the very last result before we go into our specific results is the almost product structure. These are mappings that take a vector field on M and yield a vector field back, and they have 3 properties. It's not plus or minus identity. It's a little too easy. But a square is. Not only that, just like with the linear isometry thing, if phi appears twice in the metric, you can just drop it. That's pretty nice. Now, a Riemannian manifold with an almost product structure is called an almost product Riemannian manifold. Okay, so that covers all the preliminary stuff. Let's actually get into our research. So, me and Dr. Sayar, we are going into the pointwise bislant Riemannian submersion. What is that? Well, it's a Riemannian submersion from an almost product Riemannian manifold here to a Riemannian manifold here. And we can break down the kernel, those vertical vector fields, into 2 distributions here, d theta 1 and d theta 2. These are orthogonal and pointwise slant distributions. What does that mean? Okay, orthogonal is defined exactly as it is earlier. If you take any two vector fields, from one from d theta 1, one from d theta 2, when you plug them into the metric g, they're always going to be 0. And not only that, they have this pointwise slant property. That means if you take any two of these vector fields in like the generating set, like we're thinking about the span, these are distributions, so we write them as a span of vector fields. If you take any two of those that generate that span, not only will that always be the same angle defined in this manner, totally in analogy with an angle in R3, not only will that angle between any two of those be the same, but it will also be a function across your manifold M. This is a generalization of already existing submersions in the literature, where, say, one of these distributions has dimension 0, or they have specific values, like maybe theta 1 is 0 or pi over 2 or something. Maybe both of these distributions exist, but they're both constants. These angles are both constants. This is a generalization of all of those submersions. Okay? So let's show that these actually exist in the first place. To do that, we're going to need some Riemannian manifolds and an almost product structure on the big manifold. And then we need a Riemannian submersion that turns out to be our special type. So first, let's get these manifolds all figured out. Consider R8 and R4, our big manifold M being R8 and the little one being R4, with their typical Euclidean inner products G8 and G4. Okay, now let's define these mappings here, phi1 and phi2. We can break down any vector field into their Euclidean components, x1, x2, and x8, through x8, I should say. And these mappings just swap around these components, maybe add some minus signs. And fairly trivially, these turn out to be almost product structures on R8. And they have this nice property here, where if you swap around labels, you get a minus sign. Okay? But let's get a little bit more. Those are fairly simple, almost product structures. To do that, let's take these functions f and h. Okay? F and h, just functions on R8. And clearly their sum of squares is 1. Now, if we define this mapping, phi being this linear combination, of phi1 and phi2 with these functions in mind, this actually turns out to be an almost product structure. How is that true? Well, it's clearly not plus or minus identity, but its square is. Just using our identities with the sum of squares being 1 and the swapping identity that we discussed earlier. And in fact, we can also drop phi in our metric. It may look a little messy on the slides, but indeed this is possible. This is done using like that bilinearity found from this being like locally an inner product. And so indeed, this phi is an almost product structure on this manifold R8. So we now have an almost product Riemannian manifold. Cool. Let's get a mapping from this almost product Riemannian manifold to Riemannian manifold R4. This is the mapping pi that we want to define here. It's clearly surjective, which is great. But not only that, this indeed is a Riemannian submersion. Let's show that by showing that it's of maximal rank, and it's that linear isometry on the horizontal distribution. The maximal rank thing is actually really nice. You just take the components in R8 of a given vector field, take the Euclidean components in R8, I should say, and you write them in terms of the components in R4, and you get this matrix after all of that. And this matrix indeed is of maximal rank. It's of rank 4. So pi is maximal rank. And not only that, this matrix helps you figure out the vertical and horizontal distributions that you need to verify the second property of Riemannian submersions. So, in doing this, the kernel of pi star, just by plugging in stuff into that matrix, you can show is this span here of Euclidean components. And just by taking inner products and finding orthogonality, or I guess using orthogonality of these Euclidean components, you can show that the horizontal vector fields are all given by this here. Kernel of pi star purpose given by this. Now, if you take any two vector fields that are some linear combination of these guys here, you can actually show just by plugging in these vector fields into the matrix and then plugging them into the Euclidean metric on R4, you can show that this property is true. You can drop the pi stars in our metrics. And so indeed, this is a linear isometry on the horizontal distribution. And so this pi is a Riemannian submersion. To show it's our special submersion, the pointwise Bieslein Riemannian submersion, you need to break up kernel pi star into those distributions. So let's try that. We write these distributions here. D theta 1 is this first span on top, D theta 2 is the second span on the bottom. They clearly sum to kernel pi star, but not only that, because there's only two that generate the span, two vector fields, the angle between any two that we choose is going to be the same, and their functions across our entire manifold. This is done for d theta 1 just by calculating the angle between these two guys right here. Turns out it's actually quite simple, just related to h here. And a very similar calculation shows that theta 2 is also related to f, very, very simply. And so indeed, this is a pointwise Bieslein Riemannian submersion. And so they exist. They exist already. And in our forthcoming paper in the Turkish Journal of Mathematics, we explore the general properties of this pointwise Bieslein Riemannian submersion. The general one's not of this specific example, but of a general one. And the properties we explore could be like integrability conditions, conditions for totally geodesic foliations, polyharmonicity, all of that. And so that is it. Thank you very much.